In this video, we will derive the final equation for motion in one dimension. This equation removes the dependence of time in our motion analysis. Let's begin our derivation with equation 1, which defines the final velocity being equal to the initial velocity plus the product of acceleration and time. We can also write this equation in terms of time as a function of velocity and acceleration. Now let's revisit equation 2, which defines the final position being equal to the initial position plus the product of the average velocity with time. So let's now replace the time in this equation with the time from equation 1. Expanding all of the brackets out gives us the following. This equation can be rearranged to give us an equation for the final velocity and becomes our fourth and final equation for one-dimensional motion. Of course, this equation can be written in terms of the displacement of the motion as well. Let's revisit the helicopter problem, where a rescue helicopter drops an emergency kit to a broken down boat at some distance below. In the example in the video for equation 3, we determined that this distance, or displacement, was 20 meters. Now let's use equation 4 to calculate the velocity at which the kit hits the water. The answer should be 20 meters per second as determined previously. So what do we know about the problem? The kit's initial velocity was 0, the acceleration was 9.8 meters per second squared downwards, and the displacement was 20 meters beneath the helicopter. We also defined the downward direction as positive. Let's apply this information to equation 4 by substituting the values for initial velocity, acceleration, and displacement. The answer is also 20 meters per second, which is consistent with the answer in the previous video. The Ford Mustang Boss 302 has a top speed of 259 kilometers per hour. Assuming that it can maintain an average acceleration of 6.2 meters per second squared, how much distance does it cover going from 0 to its top speed? Our final equation of motion defines the final velocity being a function of the initial velocity, acceleration, and displacement. This equation is useful when the time of the motion is not known. To recap our equations of motion, we used the definitions of velocity and acceleration to derive 4 kinematic equations that can describe the motion in a straight line. Equation 1 does not include displacement as a variable. Equation 2 does not include acceleration. Equation 3 does not include the final velocity, and equation 4 does not include time. When used in combination, these equations of motion are all that are really needed to describe motion of objects in a straight line.